So this is Prashanti Chanda, the founder of ProviLogic. So let's start the first webinar in ProviLogic. We are starting with the advanced UVM, and our aim of the today's session is to provide the importance of UVM in design verification. Like most of the students are struggling with the system verilog and UVM, and what are the things we need to focus for interview purpose. Okay, and how are the things going on in industry, and what are the important topics we need to learn from UVM or system verilog. And most of the students are okay with the system verilog. Okay, but struggling with the UVM, trying to understand the concepts in depth. Okay, because the complex concepts of UVM is mostly facing a lot of struggles, right? So that's why I want to make the concept simple today for UVM. Maybe we cannot cover all the topics in one session, in one 2-hour session. It's a 2-hour webinar, right? But at least I want to give some insights into the UVM, how to learn the topics easily, and to make the concept simple, and the difference between system verilog and UVM. Okay. So meanwhile, in the session, whatever the doubts you have, so you can ask your doubts, make it interactive. Okay. And we can discuss more into system verilog, UVM, and into the industry. Okay, so what are the industry requirement, and as a verification engineer, what is the main role, and how we need to develop the test benches or test cases, what are the industry approaches we need to follow. So we will discuss this everything in today's session. Okay, so today's session agenda is, first we need to understand what is mean by UVM. What is the importance of UVM in industry? Because already we have system verilog language. We are working with system verilog and trying to develop the test benches, different test cases we are developing. But still, why UVM is so important compared to system verilog? What are the limitations we are facing with the system verilog, and what are the advantages of system verilog? Okay. So next we are going to discuss difference between system verilog and UVM. And then UVM concepts like the TLM ports or factory registration concepts or configuration database, virtual sequences, the RAL model, and there are different concepts we need to know in how the UVM verification is done in SOC level or IP level. Okay, so we will start with the limitations of system verilog. Before that, can you tell me what are the features of system verilog and what are the limitations you are facing in system verilog while writing some codes, while writing some coverage analysis, or whenever we are generating some packets, some large transactions, small transactions. So what are the limitations you are facing, like what you are thinking to be something upgrade of the system verilog, so if it will be beneficial. So can you explain anything, the use cases? Anyone? So how many of you know system verilog from here?
Coming to the mailbox, ma'am, actually we're completely dependent on the, in order to connect inside a single language, you are going to connect that mailbox is fine, ma'am. But when you are talking about different language like system C, when you wanted to connect with the system C and other languages, it is not possible through the mailbox. So we are using TLM there in UVM, and as well as there is no interoperability available in our SV.
Okay.
And that test bench environment what we are developing in system verilog is completely dependent one. That in UVM we are going to be make it as independent of that one, as well as test case are developing independent of the test bench.
Okay. Okay, that's
and
good.
and as well in that we don't have configuration facility there in system verilog. that is available in the UVM
Okay, fine.
through.
Wait, just wait. We'll give the chance to remaining. Yeah, anyone. What are the limitations you have faced in System Verilog and what are the best features in UVM?
Synthesis limitation,
Synthesis.
limitation, like
Okay.
the dynamic data types that we could use in UVM, it is not as effective in System Verilog.
Dynamic data types in UVM means do we have any extra data types in UVM other than
I mean,
System?
in System Verilog, it is not as featured, but I think so it is there in UVM.
Okay.
In SB, we need to write all the test bench components from scratch, but by help of UVM, we could able to create usable TB components by extending the readily available classes. So that is one of the advantages.
Okay, fine, good. Okay. So I think most of the remaining students, there are I don't know whether you know System Verilog or not. Okay, maybe from today's session you will get some insights into the System Verilog, how we write actual test benches and detail about UVM. Okay, so if you're talking something or if you have doubts, then only please unmute your system or else please mute your computer. Okay. So coming to the introduction to UVM. So first of all, what is meant by UVM? UVM is a methodology. It's not a language, but System Verilog is a language specially designed for verification purpose. Okay. In Verilog HDL also we can do the simulation, but it's not dynamic in nature. We cannot connect the object-oriented program or the class-based verification in real-time environment. Okay, so to connect with the real-time environment with the complex IP designs or in SOC level, we have used System Verilog language. Okay, though we are connecting everything in dynamically, we have a lot of disadvantages with the UVM. With System Verilog. That's why we are moving to UVM. Okay, so UVM also it's a class-based verification and also it contains the libraries. Okay, and also it is well developed, structure constructed and reusable compared to the System Verilog verification environment. In System Verilog also we can reuse the test benches but not effectively. Okay, whenever you want to reuse something, we need to develop everything from scratch. But in UVM, we don't need to develop everything from scratch. We can reuse the libraries. We can make use of libraries, configuration, DB, and we can utilize the code efficiently. Okay. So in simple words, UVM consists of set of base classes with the methods and System Verilog verification environment can be developed by extending these base classes. And also it consists of different types of libraries, predefined libraries. Every functionality is predefined. In System Verilog, if you want to write some functionality for driver or for generator or any monitor, we need to develop from scratch. Okay, for any IP, we cannot reuse the same IP to next another IP. But in UVM, we can reuse the code. So how we are going to reuse the code, we will see. And next, coming to the limitations of System Verilog. So what are the major limitations we are seeing in System Verilog? First thing is lack of standardized methodology. In UVM, why we are calling it a methodology in the sense, by using System Verilog language, of course, the UVM is developed from System Verilog language. Okay, so in language, whatever the constructs we are using, whatever the limitations are there, so we like our engineers are designed it into a methodology. Okay, that means where we can use set of base classes, libraries, everything in a one point. Okay, in like everything in the parent class libraries. Okay, so that's why we call it as a standard methodology. And next, scalability issues. In System Verilog, we have a lot of scalability issues where we cannot reprogram, we cannot use for different designs or IPs, and limited reusability and transaction management using mailboxes and queues. So one thing in system Verilog, we use the mailboxes, right, for communication between one component to another component. If you are communicating within the components, we use the queues. Okay, but what are the limitations in the sense it doesn't follow some basic rules like protocol rules. So whenever we are trying to connect with the multiple IPs or multiple blocks, the two-way communication is needed or one-to-many communication is needed. But in system Verilog, we don't have those type of features, okay, by using the mailbox. So that is one major limitation. And debugging and reporting. So in system Verilog, whenever we are debugging something in the test bench, so we need to write multiple number of statements like simulated directives or any system task for every line to line. If you want to observe the debugging or if you want to observe the flow of execution, so we need to write lot of display statements or dollar monitor statements, everything. So where we got the particular error, so we need to check. So that is not much effective. Okay, but whereas in UVM we have a reporting mechanism, so automatically we will get the error report or any info report or warning statements automatically by using the reporting mechanism we can generate. Okay, so that is one limitation with the system Verilog. And next thing is no built-in verification utilities. We don't have any built-in methods in system Verilog compared to UVM. Okay, so by using all these limitations, how we are going to work with the UVM, how effectively we are going to generate the test benches. So everyone know UVM is the best methodology compared to system Verilog. UVM have lot of advantages. UVM will work at SOC level or IP level. We can easily reuse the program and it is scalable. Everyone know these things, but how to learn? How to learn effectively? So whenever we are facing some interview, how detailedly we can explain to some interviewer. Okay, we should the concept explanation is very important to the interviewer, right? So whatever you understood, we should not just understand the theory, something definitions. It is not like that. If you learn some definition, it doesn't work in real time. So whenever you are writing some test bench, it should be like a story. So where which one is connecting to which and how we are connecting, why we are connecting, and what are the ways to implement the particular thing. So when you are writing some test bench, first of all, writing the test bench is a very difficult task. Okay, so we cannot write the test bench as simple as possible. So at least if you want to write some test bench, we must have the concept clarity. Okay, so whenever we have the concept clarity, at least we will try to write some test bench. Okay, so without having the concept clarity, so where we are connecting, why we are connecting, why we are using these things and how it is implementing, without having the clarity, we never write the test benches, even if you have 5 years of experience or 2 years of experience, whatever. Okay, so for that purpose, just today I want to give some concept clarity on UVM. Maybe I cannot cover all the concepts in today's session. Maybe in future we can discuss more about UVM. So whatever I can able to cover in today's session, the basic of UVM understanding. So I want to discuss more clearly with you. And what are the doubts you have? Please ask your doubts and we can discuss on some industry standard. Whatever you know, you can share your experience while writing some test benches, whatever you face something. So you can share. Okay. And coming to the advanced features of UVM. So what are the advanced features of UVM? First of all, reusable test bench architecture. So how we are writing the reusable test bench architecture? So suppose there are different number of IPs. Okay, so in SOC. Before that, can you tell me what is the difference between a IP in SOC? What is the difference between IP or SOC?
IP is a single chip, ma'am. SOC contains different number of IPs. Number of IPs on a single chip, that is SOC.
Okay. Others, any answers? How many of you don't know about SOC or IP?
In SOC, we have
Group
multiple
of
interfaces,
subsystems.
multiple
Group of
IPs.
subsystems.
Group of subsystems.
Yeah, with the help of Ambabus, we can integrate.
Okay. So SOC in the sense is a system on chip architecture where SOC have multiple number of subsystems as he told, and in subsystems there will be multiple number of IPs. In IPs there will be different logical blocks, the digital blocks. So IP1, IP2, IP3. So this is what the subsystem. Okay. So all the IPs we need to design. We will discuss about the IP in the coming slides, like how we need to buy the IP from IP vendors and how we are creating the UVC component. We will discuss one by one. Okay. So reusable test bench architecture in the sense, so whatever we have created for one test bench, we can create multiple copies of the same test features. Okay. Suppose you have created one AXI. The AXI we can create another for another SOC implementation, and we also can connect the AXI features to the APB or AHB. So we can reuse the features. Okay. According to the whatever the specification we have, we can reuse the components. So that is what the reusable test bench architecture. Next thing is a TLM porter, TLM modeling. Okay, in system Verilog, we have a mailbox concept. Mailbox concept is like communicating between the one component to another component, right? So TLM port is also same as a mailbox, but it follow particular rules. Okay, so we will discuss that thing clearly. And phased execution model. In system Verilog, the statements will be executed normally. Like we have different regions, active region, inactive region, prepone region, postpone region. There are different type of regions, but not, they doesn't work effectively. Okay. But in UVM, particularly for execution purpose, we have phases. Okay. In which phase what should be executed, in which phase we need to take the instances, or we need to create the components, or we need to connect the components, and when the simulation need to run. So everything will be divided into particular time slots. That's what we call as a phases in UVM. Okay. Next thing is automation and configuration. In system Verilog, we don't have any configuration. That means, suppose in system Verilog, we have agent, or we have some monitor or driver, generator, or even scoreboard is there. So is it possible to enable or disable the scoreboard? Or is it possible to enable or disable the coverage report in system Verilog? It's not possible. But in UVM, we can configure anything. So which driver need to communicate to which driver? Suppose there are multiple number of drivers. So how many number of agents should be active and how many agents should be inactive? Okay. So in agent, we have passive and active. I'm not talking about that thing. So how we can disable or enable the agent, or how we can disable or enable the coverage report or some scoreboard, everything we can configure according to our requirements. Okay, so that is one of the best feature in UVM. And next, built-in verification utilities. Everything is built-in methods. Okay, so everything like libraries, the built-in libraries will be there. We no need to struggle to write actual functionality of the component, of each component. Suppose example sequencer is there. We never write the sequencer logic. Sequencer is a communicator between sequence and the driver. It works as a mediator. But do we write the mediator logic? No. We just create the sequencer. Everything will be taken from the predefined libraries. Okay, like that several examples are there. So where we can use efficiently all the UVM libraries, UVM sequences. Okay, and next, factory mechanism. One of the most important topic, factory mechanism. Like we need to create the classes. In system Verilog also we do create the class by using the constructor, right? But in UVM, Why do we use the factory registration? In the sense to override the data types, to override the objects. Suppose if there are multiple number of data types, whenever you are considering the different number of test benches, number of transactions to give the best coverage report, then overriding is very difficult in system Verilog. We need to take multiple number of statements, multiple number of different data types we need to define. But in UVM, we no need to use that. Like just we can use simple concept like factory overriding. Okay, and also it is used to create the object and also classes, and we can use the do-book methods, the copy, clone, compare, all the methods easily by using the factory mechanism. And next, advanced debugging and reporting. Advanced debugging in the sense that's what we discussed before. In system Verilog, while we are debugging something, the test bench, the test flow, we face lot of errors. So to debug those errors, we need to write lot of statements, particularly every line to line, because we don't know which line we get the error, right? So for that purpose, we write dollar display statements or monitor statements to every line to line. But in UVM, we don't need to bother about that. Okay, debugging is very simple, and also by using reporting mechanism concept, we can write any statements easily. Like automatically, it will generate the number of UVM errors or UVM info statements or warning statements or any like errors or there everything it will be generated in a table or in a tree model. There are different models in reporting mechanism. Okay, so these are the best features of UVM. Another best feature in UVM is RAL model, register abstraction level. Okay, so RAL model is nothing but whenever we are designing the memories. Okay, so in memories, every data will be in a registers. Registers in the sense address, data. So particular address. So what will be the data? The data will be different, right? There will be register files, memory mapping will be there. So compared to normal data, the RAL data, the register data will be different. Okay. So to randomize exactly the register data type, register data, we use the RAL model. Okay. So this end of the session, we will discuss clearly how we can do the how we can generate the stimulus for RAL model in register transactions, everything. Okay. So till here, everyone have the doubts? Any doubts? Any doubts still here? No? Okay, fine. So next thing is the majorly every student need to focus. Okay, like when we are attending some interview for the freshers, the first common question is what is the difference between system Verilog and UVM? Okay, so okay, we will answer system Verilog have generator, driver, monitor, scoreboard. UVM have some sequence driver and the phases will be there. So this is what just we answer. But exactly what is the way of implementing something in UVM? What are the exact differences between system Verilog and UVM? Okay, so how we can impress the interviewer. So whenever we are talking something, whenever we are telling something, so he must attract with some words. So when he attract the for the words in the sense whenever we deliver properly, okay, whenever the content is in proper deliver, then we can impress any interviewer based on our knowledge and skill set. Okay, so if you want to impress based on your skill set, first you need to understand the concept properly. Whenever you understand the concept properly, then you can easily answer the questions, any question. Okay, even you, if you don't know, you can do something right at the time. Okay, so first of all, system Verilog test bench architecture. I think most of you know how the architecture will be represented in system Verilog and what are the different components available in system Verilog. Okay, so is my PPT available, visible everyone?
Yes, ma'am, it is.
Okay,
Yes,
okay,
ma'am.
fine. So first of all, in system Verilog, we do have generator. So what is mean by a generator? First of all, why do we write the system Verilog test bench architecture? In Verilog also we are doing the simulation, right? But whatever we are writing in Verilog, it's not much useful, and also it never do the verification with the complex IPs or SOC, even a complex circuit. Okay, so that's why we are taking everything in a real-time environment by using the system Verilog. Okay, so this is our design. DUT. DUT is the design program, and test bench top is the test bench. Okay, so where we are generating some stimulus. Okay, so in the test bench here, we need to generate the stimulus. Suppose address data is there. So address equal to some value, data equal to some value. We need to generate and we need to pass the DUT. Then DUT will work according to the input stimulus, and it generate the output according to the functionality. Okay, so for that purpose, we are creating some architecture. Okay, in system Verilog. Why? Because everything we are converting in a connecting in a real-time environment with the SOC or IP, some blocks. Okay, so everything is dynamically connected. Okay, so first thing is generator. So what is meant by generator?
Generator is going to generate the data items, which means the stimulus what we wanted to give to our DUT as that was generated by our generator. The randomization happens mostly here, and that randomized data got sent to the driver through the mailbox.
Okay, fine. Any other answers? Okay, so first, yeah. Okay, fine. So generator, by using the generator, we are randomizing the n number of stimulus, like address equal to some value, data equal to some value, the control signals, write, read, or some reset signal, everything we need to generate the stimulus from the generator, and we are passing the data to the driver via mailbox. Mailbox is a communicator between generator and driver. Okay, you already know what is the concept of mailbox, right? Can anyone explain what is the concept of mailbox? Why? What is the use? Can't we send directly the generator to driver? What is the necessity of mailbox here?
No, ma'am. Actually, while we are connecting the two different components, those are working in two clock cycles are in a different clock pulses. So we need a proper synchronization between them. For that, we are using mailbox. Why mailbox? It has a built-in methods like put and get. Like it was a bounded FIFO. That bounded FIFO is going to be, it will grow and shrink according to our data which was generating by the generator. It's going to put by using a put keyword. And after all, we are getting that inside the driver by using the get through the transaction itself, the data item, the complete data item we are going to put inside our mailbox and get inside our driver. That functionality, that mechanism is provided by our mailbox.
Okay, fine. So here generator is working at some frequency, driver is working at some frequency. Maybe generator is working at a high frequency and driver is working at a low frequency. Okay, so to make the synchronization between generator to driver, because whenever generator is sending the sequences fastly, but driver is not able to access quickly all the sequence one by one, and it also need to send to the DUT. It takes some time, right? So whenever it not able to drive all the sequences fastly with respect to the generator, it lost the data, right? So in the middle of the sequences, it may lose some of the sequences. It may not able to drive all the data to the DUT. Okay, so if here 20 number of sequences are generating by generator, then driver is not able to access 20 number of sequences in that particular time. Okay, so for that purpose, without making the process fast, we are just putting all the data into the mailbox. Mailbox is like a FIFO concept. Okay, so FIFOs are same. We just store the data temporarily. Okay, so here we are storing one by one data into the mailbox, so the driver can access one by one transaction. Once it is able to drive the data to DUT, after second one it will be getting from the mailbox. After second one, again third one, again fourth, fifth, like that one by one transaction it will be getting from the mailbox, so that we never lost the data while transmitting from driver to the DUT. Okay, and also through interface. In Verilog HDL, we do connect the interface. That's a very simple one. This DUT. We write a DUT and just connect the port list. Okay. But in System Verilog, we create the interface. That too, interface is a static in nature. Static in the sense we cannot change in runtime, because here generator is a dynamic in nature, driver is also dynamic, monitor is dynamic. That means everything will be changed in runtime, and also we are creating objects. Through the objects we are accessing everything. Okay, but interface is not a dynamic. For that purpose, we are creating virtual interface. Okay, virtual interface. Through virtual interface, we are driving the data from driver to DUT. Okay, so that is what the concept. And here the transaction is there. So what is the transaction here? Transaction in the sense, whatever the data we are going to drive from generator to driver, driver to DUT, all the data we are putting in the transaction. In the transaction, we write the randomization, constraints, everything. Okay, so transaction is it's a component, transactor. Okay, and so now DUT got the stimulus from the driver, so it do the functionality. According to the functionality, it give the output. Okay, so that output will be sent to the monitor. Okay, so monitor will receive the particular output from the DUT. Whatever it receive the input and output data, we need to observe at the output side, at the console, right? So to do that, the monitor is sending to the scoreboard again via mailbox, because it cannot send directly to another component, right? Here one component to another component, whatever, generator to driver, driver to monitor, or driver to scoreboard, whatever. To make the communication between one component to another component, we use the mailbox for synchronization purpose without losing any data. Okay, so now monitor will send all the output and input data to the scoreboard. From the scoreboard, we are able to check the output, whatever displayed at the output waveform or at the console or transcript, whatever. Okay, but in System Verilog, we have another advantage called scoreboard checker. Okay, so here in scoreboard, we will check the output, right? So whether it is matched or expected value or not, we will check with the scoreboard. Okay, so these things we are running in a environment. Environment is a top level. To the top level, another to the top level of environment, it's a test. Okay, so the test and interface will be run from the test means top level, top. So I think hope you know the concept of System Verilog. So quickly we will get into the UVM architecture. Okay, so in System Verilog, it's a basic architecture. Like one master is driving the data to DUT, suppose. Okay, so if you connect to the master and slave, and then master will drive the data to DUT, and from DUT to we'll get the slave That is another concept. Okay. So in UVM test bench architecture, what are the major differences with the system Verilog compared to UVM? First of all, first difference is in system Verilog we have a generator. Generator is used to randomize the data, input stimulus and send to the mailbox. That is what the task of generator. Okay. But in UVM, we use a sequencer to driver. Okay, so why do we use the sequencer? Why not generator in UVM? Can anyone tell? Why do we use sequencer in UVM? Why don't we use generator? What are the limitations?
In generator, we are randomizing. So that code, what and all you are writing, it is a standard one. So we cannot change anything there. But in UVM, outside sequence, we are randomizing inside that task body. We can change the test cases. But here the sequencer is completely already built. It was a virtual class of UVM, and we are extending it. That code complexity is also reduced here.
Okay, fine. Any other answers? Others? Can anyone respond? Shranay, Vishal, Madhumita. Why do we use the sequencer instead of generator? Okay.
In the sequence, like sequencer uses the multiple sequences. Those sequences actually we can use in different test benches and different tests. So that's why we use a sequencer, because that those sequences can be used anywhere in the test, many tests. So
In the
reusable.
sequencer we can control the flow of signals. Coming to the generator, we can't control the flow of signals.
By
Okay.
using virtual sequencer, we can handle the sequences.
Okay, fine. Okay. So first of all, whatever the transactions we are using, the transactor in generator in the system Verilog, okay, compared to UVM, UVM provide proper library for the transaction, UVM sequence item. Same, whatever the transactor is there here, in UVM also we have a transaction class. That's what we call as a UVM sequence item. UVM sequence item extends from, sequence item extends from UVM sequence item, which is a parameterized class. Okay, so and also here, if you see base sequence is same as a generator. In the sequence, we will generate n number of sequences and send it to the sequencer. Okay, so through the sequencer, the data will be sent to the driver. But what is the major use? Why don't we use the generator in a sense? Sequencer is first of all high level, and also it connects the lot of sequences. Suppose in UVM, mostly we will connect with the system on chip. Okay, suppose in SOC, there will be n number of IPs. One IP is related to AXI, one IP is related to AHB or APB or PCIe or USB or any graphic processor, GPIO or CPU, whatever. Okay, so whenever we are buying some IP from any IP vendor, they will provide the UVC with the sequences, okay, directly. We no need to bother about the design or anything. Okay, so whenever they are providing the UVC, everything will be the sequences, whatever they are providing. So all sequences we need to connect with a one sequencer, all physical sequences to one sequencer. That's what we call virtual sequencer. Okay, so by using this virtual sequencer, we are going to drive actual stimulus to the driver. Okay, so here no need to worry about how we need to design the any IP or any AXI design or any APB or PCIe design. We no need to bother. Whenever we are buying with some IP vendor, they directly provide the sequences and number of sequences. Those sequences we are connecting with the virtual sequence and virtual sequencer to the physical sequencer or sequence. So through that we are going to drive. Okay. So for that purpose, that is the major advantage. But in system Verilog, we don't have that advantage, right? So we never connect all the IPs to one single generator, and the generator will never drive all the data. Okay. So that is the main advantage of UVM sequence or sequencer. So by using sequence and sequencer here, we are trying to divide the task into two different levels. Okay, so sequence means n number of test cases, it generate n number of test cases. So what one is a simple task, and the sequence item same as a transactor, and sequencer is a mediator between the sequence and driver. Okay, and driver is driving the stimulus to the DUT, same as system Verilog, no change. Okay, but another change is here we are using TLM port connection. Okay, if you see here port and implementation port or export, we will discuss that thing clearly. Okay, so whenever you get the interview question, all the freshers, okay, so first of all you need to start from this basic point, from generator to sequencer difference, then mailbox to TLM port difference. Okay, whenever we are driving the data from DUT to monitor is connecting to the scoreboard. In system Verilog also we connect monitor to scoreboard, monitor to coverage. Okay, and if you want to write extra checkers, we can connect monitor to checker, but every time we will create the mailbox for scoreboard to monitor, mailbox for coverage to monitor, and mailbox for any different components, whatever. Okay, so we need to create multiple times mailboxes. That too, it's not a bidirectional and it doesn't follow the proper rules. Okay, the consumer and producer, it doesn't follow the proper rules. But by using the analysis port here, if you observe, monitor is connected to scoreboard, parallelly monitor is connected to coverage by using the TLM analysis port. Okay, that is the one of the advantage in TLM ports. Okay, another thing, the third difference is in system Verilog we use the and the interface and virtual interface same as normal system Verilog and UVM, and the basic environment UVM environment, everything we derive from UVM libraries, and sample based test. So this test is same as the test here. Okay, sample based test, and this test and interface will be run from the top module. Okay, so these are the major differences from system Verilog to UVM. And conceptually there are a lot of concepts like phases or config DB. Here monitor to config DB also we will connect. Okay, one configuration database file, or RAL model, we will connect to RAL model. So where when we have the register sequences. So these are the common differences. Everyone understood till here? Is it clear, everyone?
Yes, ma'am.
Any doubts?
No, ma'am.
No? Okay.
Can you please tell me once more virtual sequencer? Here I think virtual sequencer is not there, right? But you used to that one.
Virtual sequencer?
Yeah.
Here, okay, in this slide, virtual sequencer is not there, but in the coming slides, we will discuss virtual sequencer. Okay.
Yeah, sure. Thank you.
Next, UVM test bench architecture at the IP level. So if you want to verify any particular IP or any SOC, so how the test benches will be, test architecture should be written. So whenever you are writing some test bench, suppose AXI protocol is there. Okay, so for AXI protocol, if you want to write UVM test bench, first of all, we need to draw the architecture. we need to draw the number of test cases. So which feature you want to verify, and what are the values in terms of constraints, what are the address value, data value, or any signals. How so we should have some plan. Okay, so which values we need to generate the coverage report, what are the bins we need to write. So everything will be detailed plan. So first of all, how we are going to draw some architecture in IP level, we will discuss that. So if you observe here, first of all, in a IP, it consists of register and also normal sequences. Okay, that means it has some memory and also normal VIP. Suppose there is a memory this one is a IP or any subsystem. In this subsystem, we have a RAM memory, okay, or any register based memory file, and also another IP like AXI protocol or UART protocol, simple protocol, whatever. Okay, so it requires two type of sequences now. One is a normal base sequences, binary sequences. One is a register sequences for the memory. Okay, so how we connect the register sequences? So register sequences will be taken into the register sequence library, and custom sequences. Custom sequences is for normal IP, for protocol, suppose your protocol. Okay, and VIP sequence library. VIP sequence library in the sense, if you have particularly any VIP or like AXI VIP will be there, or AHP, any particular VIP for that one sequence. Okay, so all the sequences, suppose normal sequences means directly we will send the sequence to the sequencer like this. These are normal VIP sequence or any protocol sequence. This sequence directly sent to the basic sequencer. Another thing I forgot, in UVM we have the agent, but in system Verilog we don't have the agent. Agent means it is a one abstraction layer, extra layer, which consists of sequencer, driver, monitor. Okay, based on the transaction type, if you want to use active agent or passive agent, we can enable or disable the monitor, sequencer, driver. If you want to connect all the things, you can connect, or else we can disable. We can just simply use active agent or passive agent. Based on the configuration DB, we can configure. Okay, so here these virtual sequences and custom sequences are normal sequences. So we are directly sending to the VIP agents. Okay, but coming to the register sequences, I will discuss clearly at the end of the session the register sequences, how we are using adapter. Adapter means the sequences can be converted into the bus sequences. The register data will be converted into binary data. Okay, so through the adapter, we are sending the sequence to the sequencer and the driver and to the RTL block. So in design, we have a RTL block and also another user IP block. Okay, and for this user RTL, like your protocol. So for your protocol, we are taking the sequences from VIP and sending to the agent. In agent, we have the sequencer and the driver. From driver, we are sending the data to the normal UART protocol. Okay, and also we are designing a checker. Okay, checker in the sense a scoreboard. Okay, just to check what is the expected value and what is the whatever the value we are going to check, comparison value. Okay, expected value and comparison value in the checker. And config. In config DB, we can write any specifically user defined. So if you want to use any type of agent, or how many number of agents you want to use, or if you want to enable or disable the scoreboard, or whatever the data set, by using the set and get methods, we can design the configuration database. Okay, and this is what signal interface driver from the custom sequences, from normal sequences. Okay, so this is how we will design a UVM test bench architecture in a design, in a SOC design. Okay, here down one is a IP or system on chip design. in a IP, just considering two design blocks. One is a memory type, one is a normal. Your any design like a Bluetooth or some any IO port. Okay. So how you are going to generate the normal sequences and register sequences and combining to the design. Everyone clear at the till here? Everyone clear? Any doubts?
Ma'am, here, where is the monitor here? Like,
Monitor will be in agent.
it's register bus agent.
Sorry.
In the register bus agent?
See here, agent. Here you are telling monitor. Huh?
Like it, driver is sending, and but from where, from duty will send back to the
Here
testing wire.
we didn't have the monitor, but from the DUT we can connect the monitor to scoreboard and monitor to coverage collector. Here there is a coverage collector for
Yeah,
register
the bus
monitor.
collector is there. Yeah,
Yeah, we
that,
will connect. And here also we can connect another monitor to scoreboard. Here checker is there. So monitor to
yeah,
checker.
yeah. That's why I have asked. I thought it's purposefully it is not written or something like that.
Okay. And also make files in the sense all run methods we will put into one make file, whatever the required files are there, everything we will put into the make file and run through the script. The coverage commands or regression commands, everything we'll put into the make files. Okay, any
Hello.
doubts, everyone? Yeah, please.
Hello. Hello.
Yeah, you are audible.
Yeah, usually in every IP there will be a resistor.
Every
Hello.
IP, yeah, please tell.
There will be resistors, right? So for every IP, do we have a RAL model?
So wherever the registers will be there, definitely we'll have the RAL model. In IP, we have the different blocks, right?
Okay.
So whatever we are verifying
So
the particular
for
block.
every IP, yeah.
Hello.
Okay, fine. Then another doubt is here
Your
checker
voice is clear. Yeah.
and assertion both are same.
Checker and assertions.
Checker and yeah,
Checker
both are
and
same or different?
assertions are both are same.
Because
no, checker and assertions are both are not same. Checker is like a scoreboard. We can also define it like a scoreboard. Hello.
Yeah, sure. Okay, fine.
Are you talking?
No. I cleared my doubt.
Okay.
Thank you.
Okay, fine. Okay. Others, do you have any doubts? Okay. Yeah, please tell. Assertions.
What will assertions do, ma'am?
Assertions is nothing but we just validate the behavior of any design. Suppose a flip-flop is there. Okay. So flip-flop have two number of outputs, Q bar, S or flip-flop is there. S or 00011011. So at 00, at particular positive edge of the clock, whether it is giving proper output or not, correct output or not. Like that, it will check every positive edge of the clock. In the design point of view, we write the assertions, not verification point of view. Okay, just it validate the behavior of your design, whether it is working correctly or not. With every edge of the clock or with every input sequence. Yeah. Hello.
Oh, yes, ma'am. Cleared, ma'am.
Clear? Okay, any other doubts? Others? Okay, fine. Next, TLM ports in UVM. So if we see in UVM we have the mailbox concept, right? But in TLM in UVM we have the TLM port concept. So how we are going to use TLM port? Okay, so in in system Verilog, if you see mailbox to mailbox, generator to mailbox, mailbox to driver, we just use a put method and just use a get method. Okay, so driver only drive the stimulus, but generator only generate the stimulus, but driver will drive the stimulus, but it is not interchangeable. The generator never drive the stimulus to DUT, and the driver never generate the randomizer data. It never be interchanged, right? But in TLM port in UVM, we can interchange. Okay, so that is the one main advantage. Okay, in TLM, we have mainly port and implementation. One is related to port, one is related to export. Implementation port and the port. Okay, port is nothing but driving the data. In implementation, we implement actual data. Okay, so producer we call as a, suppose if it is an initiator, we have a two type of methods: locking put port and get port. Okay, so suppose here generator is there. Okay, and the target. Generator can be initiator here, and target can be export. Export in the sense it is a target which have the implementation. Okay, and here generator is a initiator. Okay, so it just receive the data by using the put method. It receive the transaction using implementation port, and producer call the put method and send the transaction to TLM port. Okay, and both are interchangeable. If you want to use generator as a target, we can use generator as a target and initiator as a driver as a initiator. Then export and put port will be, export implementation port and the port will be interchangeable. Okay, so now driver can also do the randomization. It can drive the stimulus, and generator can accept the stimulus. Okay, so both are interchangeable. We can do any way according to your requirement. Okay, so how we are connecting the TLM ports here from producer to consumer or consumer to producer? Suppose here is a target and initiator is there. Suppose this example, target and initiator. When put it is a target, then we use the get implementation method. Implementation method is a producer side, and get port is a consumer side. It's a target. And here it is reverse. Target, initiator. When it is a target, we use the put port method, and when it is a initiator, we use as a implementation port, put implementation port. Okay, so nothing but the directions. We are not just using put method and get method here. We are just putting the directions. Okay, so one is initiator, one is a target, so which can do the randomization and send the data and accept the data. So vice versa, we can do vice versa. Okay, suppose this is how we connect the TLM port, which follows the specific rules, but these type of rules we don't have in a mailbox concept. Okay, suppose my question is, if one component is working as an initiator and another component is working as a target, right? There will be no proper synchronization. There will be a proper synchronization. But suppose if both are working as an initiator, how the synchronization will be happen? Suppose here one is the initiator, one is a target. Okay, if a generator is an initiator, driver is a target, we use the put port, put implementation port, or get port, get implementation port, get port. Okay, so one is a initiator, one is a target. Suppose both are initiators, then how the synchronization will be happen here?
Using semaphore.
Using
Here
semaphore.
we have a requirement of FIFO.
Okay.
TLM FIFO is
How
needed.
do we connect using the semaphore
Using
concept here?
FIFO, we can store.
Okay. How do we connect the semaphore concept? How do we use the semaphore here? Okay. How do we use the FIFO here?
Like both are acting as an initiators, we need the two targets. So we need to get that exports, TLM exports in both
Okay.
the sides of our FIFO.
Wait
One
a
side
second.
is
Others, can anyone? There are a lot of members, so every time one person is answering. What about others? Can anyone? So what we do here? Tamanna and Vishal. CB. So can you answer? If one component is working as an initiator, another component is obviously target, or one is a target, another one is obviously initiator. Okay, so that there will be have proper synchronization automatically if one is a target, one is an initiator. But if both are initiators, then how we can design? CB.
Yeah, we can use TLM FIFO concept so that our consumer can request at the same time our producer can request can initiate. Actually, our consumer can initiate at the same time our producer can initiate, and these two will be synchronized by using TLM FIFO.
Okay. So in that case, how we are connecting the sequence and the driver?
Arbitration mechanisms can we use?
Yeah, actually, our producer will put the transaction. It will use put transaction. At the same time, our consumer will initiate for get the transaction.
Okay.
So we have put and get methods, no? So since both are initiators, our producer will initiate to put some transaction. At the same time, our consumer will initiate to get the transaction. So it will be maintained using TLM FIFO.
Okay. Okay, fine. So here in TLM FIFO concept, whenever producer is an initiator and consumer is also initiator, in the middle for the synchronizer, just a mailbox concept. Okay. So in the mailbox concept, but there we are not telling both as an initiator. Okay. But for synchronization purpose, we are putting the mailbox in the middle of generator and the driver. In the same way, for synchronization between initiator and this initiator, we must have the targets also. For that purpose, we are putting the FIFO here, and here FIFO will be the target from here. So initiator to target flow and target to initiator. Okay. So this is how we can use the FIFO concept in UVM. What are the applications? I mean, where we use this type of connection? In which cases?
like monitor and scoreboard, both are requesting the data.
Monitor and scoreboard both are requesting a data.
No, ma'am. That from monitor, from monitor, scoreboard, as well as that reference model that will be here available.
Then how we connect the FIFO? Monitor to scoreboard, reference model you told, another block. So 1, 2, 2 blocks. Then how do we connect the?
Yeah, that was not possible. I'm talking about the analysis port maybe. Yeah.
Any answers? What is the use case? Normal generator to driver, can't we use normal sequencer to driver?
Yes, ma'am, we can use, but one will be an initiator and another one act like a target.
No,
Since
both will
both
be work.
here both needs to work as an initiators.
Then which
Can use in one-to-one communication, ma'am.
This all are one-to-one communication only. Only analysis for one-to-many communication.
Ma'am, like if you are verifying that memory, that what and all we are writing, that and all we are reading. At that time, the driver data we are driving and as well as monitor data will be same. So both will be act like initiators. At that time, we will use this concept.
Okay, but driver to monitor we are not connecting, right?
Yeah, here we are
Will you
connecting
connect
from
driver
sequencer to driver.
Okay,
Ma'am,
so
here
everyone
FIFO
try to do some concept analysis on this, okay, and try to get the answer. Maybe you can send me personally. So what answer you got? Okay, so how we connect real use case in real time. So okay.
Hello, ma'am.
And coming to hello.
Here FIFO helps us to synchronization between monitor and scoreboard and predictor, which stores data in FIFO for help us to comparing.
Okay. FIFO is for comparing.
The data which stores in FIFO for help us to compare.
Can you repeat again?
It is FIFO help us to synchronization between monitor and scoreboard and predictor, which stores data in FIFO for help us to comparing.
Okay. Okay. Monitor to predictor and scoreboard. Monitor to predictor, okay, which get from the DUT. Predictor will convert the reg sequences to the database. So here FIFO is using for comparison. Huh?
Yes, ma'am.
So monitor you're connecting with the predictor and also scoreboard. Okay, monitor is the initiator, predictor is also initiator. Huh?
Here we connect monitor with analysis port and FIFO and SB, and after that we connect predictor. Right here, monitor contain analysis port and FIFO one contain analysis export, and other side get export to SB get port.
Other side in the sense predictor.
No, scoreboard.
Then what about predictor?
Here predictor given transactions, right? It is an initiator, and we using put port, and SB as an initiator we use put implement port.
Did you design like that?
Yes, ma'am. In previous one I designed.
Okay. So you're connecting monitor to predictor as a normal TLM FIFO, and two type of TLM ports you are using separately, not analysis port.
Yeah, ma'am.
Okay. But why directly we can use analysis port, right? Because initiator means we no need to get any data. Okay, predictor is going to convert the sequences for that purpose. You read down.
Yeah, ma'am. This can be at where we are having the two components. Like if you are having two components, like those two are acting like an initiators inside an environment. Uh, it consists the TLM FIFO.
Inside the environment.
Yeah, ma'am. Inside an environment, we are having the TLM FIFO, and we are connecting one component as a producer and another component of the same as a consumer as well.
Yeah, we can connect like that. Okay, fine. Next one is an analysis port. Analysis port in the sense till now we have connected one component to another component, from generator to driver or sequencer to driver, monitor to scoreboard, or monitor to coverage, only one to one. Okay, but in some of the cases we can connect a one to many also. Okay, so one to many, the most of the cases is monitor. Suppose from monitor you want to send the data from monitor to scoreboard, monitor to RAL model like a predictor, and monitor to coverage. If you are writing some coverage, there you can send, or if you are writing separate configuration database, you can send. Okay, so by using a single monitor to many, one to many. Okay, but here before we have used put port method, get port, put implementation, get implementation. But here we don't have put port or get port. So which method we use to send the data?
Right.
Write method. By using a single write method, we will send the data from monitor to different components or one to many components. Okay. But theory wise, if you are okay with the theory, you can mostly work on practical things. Okay, but if you are not aware with the theory part, just try to get a good idea. Conceptual idea is very important. Okay, so where to connect put port, when to connect get port, so how implementation, port, export is working. So these are very important things. Okay, next, UVM phases. So what is the use of UVM phases?
Basically for the synchronization purpose, ma'am. In our system Verilog, we need to write the start method as well as stop method. That we need to start all the start methods of our components inside the environment as well as inside the test as well as in the top. So in order to get rid of them, we are introduced with the UVM phases. It provides the basic synchronization when we need to create the components, when we need to connect the components, when we need to run our stimulus to our design, when we need to extract that stimulus
Remaining
as the
voice.
output from our design.
Okay.
Sorry, ma'am.
Okay, fine.
It's
And
control the execution.
whether the data is correct or not, we need to check. After that, we need to report, and the final report we need to get. That and all the UVM phases will going to.
Remaining, any answers from your
It
side?
controls the execution order and synchronization.
Okay.
That's
Okay. Suppose example, we have in a runtime. Okay, there are different run phases. Okay, phase 1, phase 2, phase 3, phase 4. In phase 1, there is a reset. So entire components or signals need to reset. In driver, we write the reset task, then main functionality task, right? Like that, right? So first reset and configuration of entire functionality, and main test execution and shutdown. Okay, like 4 phases are there in execution. Okay, so in these 4 phases of execution, there are 3 number of test cases. Okay, 3 number of test cases are there, or 3 number of components are there. Okay, suppose if you talk as a test cases for simple understanding. Okay, so here 3 number of test cases, or else 3 number of components. Generator is a 1 component, driver is a 1 component, and monitor is another component. Okay, so every component have 4 stages: reset, configure, main, shutdown. Okay, so if there is a no phases concept, suppose in generator block, in generator component, reset is taking some time and configure is taking more time. After immediate reset, it is moving to configure method here. Okay, after configure, immediately it is moving to main. After main, it's immediately moving to shutdown. Okay, in component 2, reset is taking lot of time and configure is taking less time, and main is taking this much of time. Immediately shutdown is completed till here. Okay, and component 3, reset is taking long time, configure is also taking long time, main also taking long time, and shutdown also taking long time. Okay, so first component completed its execution at this point of time, suppose, and second component completed its execution at this point of time, and third component is completed at this point of time. Coming to the final state of execution in top level environment, if all these components are not in synchronization, one is completing reset first, another one is completing configure first and shutdown, one component is shutdowning fastly, and last one is need to wait till it completes. Okay, so it is everything is a mixed. Okay, so to avoid this, internal system will get the confusion and we will not get the proper output. Okay, there will be loss of data if something is working slowly and something is working fast. Suppose generator is working fast and driver is working slow, there will be some loss of data and there will be no proper synchronization between DUT, driver to DUT, and DUT to monitor. Okay, so to avoid these things, phases concept is introduced. That means whatever the task it is, it should be completed in that particular phase only. Whether it take less time or maximum time, whatever, it should complete in that phase. Once all the components completed its phases, then only it should move to next one. Okay, like that. Suppose reset is there. Reset is a one process. Okay, so component 1 is taking less time, component 2 is taking more time, component 3 is taking some more time, like little more than component 1. Okay, but after immediate reset of completion of reset, it should not start with a configure. Okay, this reset also need to wait to complete second component, and third one also need to wait till third one is completed, so that the reset will be completed by all components. One process is completed, then only 3 components at a time should get into the configure process. Okay, so configure is taking some time, and here some less time and more time compared to component 1 and 2, but still these 2 must wait till component 3 completed. Okay, so that is particularly executing in particular phase. Like that main test execution, suppose main phase, it also need to execute in particular time. So even all the components complete its execution, remaining components need to wait. Okay, and then last shutdown. So like this, if you follow particularly in the phases, okay, so we will get proper synchronization. This concept we don't have in system Verilog. System Verilog we have active region, postpone region, prepone region, non-blocking region, blocking region. In active region, different system tasks will execute, $display, $monitor. In blocking assignment region, non-blocking statements will execute. In blocking statement will execute. In prepone, some statements. Like that, we have different type of regions, but those are not synchronized between each components. Okay, some will execute fast, some will execute slow, and some will execute in their regions and will not execute sometimes. Okay, so there are a lot of mismatches. So to avoid that, particularly phases concept introduced in UVM. Okay, so in UVM we have different phases like a build phase, run phase, cleanup phase. Okay, so build phase means suppose here generator to driver, monitor to scoreboard is there. Okay, so first of all we need to take the instances. Okay, after taking instances in the sense we just need to create the generator component, driver component, monitor component, sequencer component, just creating, not make any connection. Okay, so these creation of components will be done in a build phase, and in the connect phase we need to make the connections from here TLM ports. By using the TLM port in connect phase we do use the we make the connections, not other than that. Okay, if you want to do wherever you want, we cannot do like that. Only in the particular phases we need to do. Build phase means creating the component, connect phase means connecting the components one to many or one to one, end of elaboration, start of simulation, and in the run phase, in run phase we will execute the main task. Okay, and extract phase, extract in the sense we will extract the data from each of the component, and check phase whether we need to confirm whether it is correct or wrong, and report phase, if anything is report or errors or any warnings are there in the report phase we will get all the data, and final phase which complete the execution here. Okay, and we'll get the output. So like this, every execution, in the execution we have the test flow. Okay, so in that everything will be done in terms of phases. Okay, which one should be executed in particular time. According to the particular time we will get the data. Okay, so build phase, connect phase, end of elaboration, start of simulation, all will be comes under one particular time, zero simulation time, because all these are functions. It doesn't take any time, okay, to run the phases, but run phase consume time, so that's why we write using the task. Okay, only one phase, run phase is a task in UVM, remaining all phases functions in UVM, because all are execute at a zero simulation time or non-simulation time. Only run phase will consume the time, the delay, because in the run phase in driver, if you write, we need to drive the data to DUT. First we need to do reset task, then main functionality need to get the data from transaction and send to the DUT. There are a lot of things. Okay, so that's why it is a long run execution. Okay, everyone clear with run with phases concept in UVM?
Ma'am, I have a doubt. In regular test bench environment, what and all phases we use? Like we are not supposed to use all 20 phases, right? So
we don't need to use all the phases for normal use cases. We can use majorly build phase just to create the components, and connect phase to connect the components, and run phase. Sometimes we use start of simulation. Even if you don't use start of simulation, fine. These three are main. Okay, in remaining other phases as per the requirement, if you want to check, then only we can use, otherwise not required.
okay, build, connect, run, that's it.
Ma'am, has small door.
Yeah.
Hello, ma'am. Can I audible?
Yeah, it's done.
So basically we'll write task, in the task we can write function, right? So can we write in the run phase, can we write in the run phase, can we write build phase?
Can we write run phase?
Can we write build phase in the run phase? Like how we
Build
write in the
phase?
task in the function?
No. Build phase you want to write in run phase, huh?
Yeah. No, ma'am. Generally, we'll write in the task. We'll write function, right?
Okay.
So like that in the run- in the run-
Separately we need to write the phases. Okay, in suppose driver block. In driver block first we need to write the build phase. Connect phase is not required in driver block because connections we make in a top level. Suppose the driver monitor sequencer top level is agent. In agent we make the connections of local lower order blocks. Okay. In driver we write the run phase as a task only. We cannot
basically
write
we'll write
what?
in my question is simple, ma'am. In the task we'll write function. So the same way in the UVM can we write like phases in the run phase or any per phases, can we write build a phase in that per function? That's all, ma'am, my question. Yes or no? If yes, why? If no, why, ma'am? That is my doubt. Actually, this was the inter question.
No. First of all, just a second. Yeah, can you tell me now what is your question?
No, ma'am. Basically, in system Verilog or in Verilog, we will write in task we'll write function, right? We will say obviously.
Okay. In task we will write function.
So coming. Yes.
Inside task we can call the function. That's what we need to tell to ma'am. Easily she can understand.
Okay. Some functionality.
Okay. In the same way, in the UVM, inside the run phase, we'll write. Can we write build phase?
Inside the run phase, can we write build phase?
Yeah, as how will write function in the task.
The thing
Kalyan,
is, without building a component, we cannot able to run that specific component. So it is not possible to write
We
the build
cannot
phase inside.
write build phase within the run phase. How do we write? First of all, we need to create the component in the build phase. We need to connect the components. Then only we can drive something. Right? Run phase is nothing but driving the data, the main functionality. Okay, function is different. Task or however you are asking, I don't know. The question is wrong. First of all, we cannot put build phase in the run phase. Then what is the use of phases if you match everything?
Actually, these phases are not built by us. These are overridden by us only.
Okay. Yeah, of course. We are just using three different.
Actually, that Kalyan is saying that inside task we can call the function. As we discussed, that build phase is a function. So why can't we call inside that run phase as a task? That was the question asked in Inter. He was saying.
Okay. Then what did you answer that time? Kalyan?
I was very panicked for that question.
Then you need
it
to
was the
ask
first
him.
question.
Can you just explain?
Yeah, it was a virtual interview. So it for starting only was throwing that question.
Okay. For Kalyan only we'll get these type of questions. Okay. Next, I think everyone got clarity with phases concept. Is it clear, everyone? Any doubts still here?
Hello, ma'am.
No? Okay. So
Hello.
next, some more. Yeah.
Will write in the field phases.
Please, bit louder. Talk bit louder.
Build phase, connect phase, start of, end of elaboration, start of simulation, or we can say in this manner. Pre-running phases and post-running phases are written with the help of function. Run phase is written in with the help of a task. My question is it possible to write pre-run phases inside the task and post-run phases with the help of task? Is it possible to write pre-run phases, post-run phases with the help of task instead of using function?
No, not possible.
Why, ma'am?
Why? Because because those are executed zero simulation time. For task, we use the delays, right? So it's a long execution. For functions, these phases we can use only the functions because no need to use the delays and right. It's just a simple execution. Task means it takes lot of time to complete the execution. So that's
But
why majorly
function
we
cannot contain time-consumed construct or statements inside the function block, but the task may contain or may not contain time-consumed statements. So zero-timed statements or non-zero time statements can be written inside the task. So instead of using function, why not we go with the task with the zero-time statements?
see for build phase and cleanup phases we can use the task, but it's a long running task in the sense it takes lot of time to run compared to function. Okay, that's why we never prefer task for these phases because simply we can complete our simulation in a small execution time, right? So why don't we use put lot of time by using the task? If you write task, one task for build phase, one task for connect phase, end of elaboration, start of simulation, these all are long execution process. Okay, functions will execute fast compared to task. That's why we use the function for these cases.
The thing is, these components are basically derived from UVM objects. So if we see the UVM objects, so there all these build phase, connect phase, all functions are there. So whenever we try to invoke this build phase and stuff, we are using this super keyword to tell our components has to be part of that UVM object. That's the reason why we could not able to change those functions to task.
Yeah, that is also one reason. Mostly, but majorly the task will take lot of time. That's why we use the function. Okay, these all are predefined from objects and also the super parent class. So majorly we use function because of that reason. Okay, any other others?
Not clear, ma'am. Once again, can you repeat again, ma'am?
Hello. Okay. Next, some more important concepts we must know is a factory registration concept. Factory registration we already discussed, right? So to if you want to create a component or a object, we use the macros utils to create a component or object, or majorly to override the data type. So why do we override the data type? Suppose whenever we are considering number of transactions. Actually, we will take only one transaction in system Verilog. So by using one single transaction, it is difficult to hit the coverage. to hit the coverage bins in coverage analysis. Okay, so for that purpose we take a multiple number of transactions. Okay, whenever we are considering multiple number of transactions in system verilog, we will find like a difficulty while calling every transactions into the every component. Okay, so we need to always change its a data type. So it's a very difficult thing to change the data type of every transaction. We use a $flag argument if you observe in some cases for different transactions. So to avoid that, by using the factory registration concept, simply we can override the data type. Suppose you are creating multiple number of drivers. Suppose there is a component, block 1, block 2, block 3, and for this block we have created one agent, and another digital block created second agent, another one created third agent. Okay, so in every agent there will be a driver 1, driver 2, and driver 3. Okay, suppose if you are using some inheritance concept or polymorphism concept, okay, so this driver can be inherited by these and here. Okay, so whenever you are trying to, suppose this driver want to inherit to another one, parent to child, again if you want to override some data type or override the object name, the class name, suppose this is the child class here, and here driver 1 is the parent class, and this child class name you want to override here or some other blocks. Okay, so whenever we are trying to change, automatically we cannot change normal cases in system verilog, but in UVM we can directly change. That is what factory overriding. Okay, overriding concept. So when we are doing the registration with the object and component, so all these things will be activated, and also the hook methods are the copy, compare, clone. So all these methods we can use directly after doing registration. Just in old methods there will be lot of process to do the registration, like we need to write ID, wrap, everything, like 6 to 7 lines will be there to register a single object or any variable or any transaction item, sequence item. But by using nowadays, not nowadays, later on concepts, we are using the macro stick UVM util macro for component registration and object registration. So that is one of the important concept in UVM. Okay. So next thing is a configuration data type, database. So configuration in the sense I already told you, right? When there are multiple number of sequences or agents, if you want to configure with active agent or passive agent or particular agents, if you want to drive the data, or particular agents if you want to use, then we use the configuration database. And whenever you want to disable or enable some scoreboard or coverage report, everything we can configure from the config DB. Okay. Next thing is the reporting mechanism. Reporting mechanism in the sense, this thing also we discussed. In system verilog, whenever we are doing some debug, we need to write lot of statements, a lot of display statements or monitor statements, right, or anything. Okay, so to make easy, to make the concept easy and debugging easy, when we connect with the complex components with several IP. So by using the reporting mechanism, we can view the verbosity levels based on high, medium, low, which one should be execute and get output at the console. And also we can automatically generate what are the errors, what are the warning info statements. Okay, everything automatically it will be generated by using the report mechanism. Just we need to use $UVM info, $UVM error, or UVM not dollar macro we need to use. Okay, so that is what UVM reporting mechanism. Okay, these three concepts clear everyone. Actually, these all are very complex concepts. It is not possible to discuss in one session because there are a lot of internal concepts will be there, sub concepts, and also coding syntaxes are very important. So whenever you are writing for configuration DB, the syntaxes, so in get method, set method, so what are the data you need to drive. So these are very important. Okay, so if you know the basic knowledge, then concentrate on syntaxes, everyone. Okay, clear till here, everyone? And next thing is a virtual sequence concept. So virtual sequences are nothing but, before, as I told you, we have the UVC components. UVC in the sense a universal verification component. Okay, so UVC in the sense, suppose here there is a SOC. Okay, in a SOC, there is a core related, processor related IP, or some GPIO, and memory related IP, or AXI related, and APB related, AHB related. There are different type of IPs. Okay, but we don't have all the IPs. Suppose there is a memory, there is a RAM memory or FIFO memory. Only FIFO memory we have a design. Remaining all IPs we don't have any design. So then what we need to do? So if we talk, actually we never design the IPs. Okay, any product based company, whatever you see, just they will buy the IP from IP vendors, VIP vendors. There will be different vendors will be there from top product based company who sell the IP. Okay, so for APB we need to buy some APB VIP, or AXI IP, or some here like AXI or AHB related, PCIe related, YOT related, different IPs we need to buy. Okay, so whenever we buy these IP, by default we call it as a universal verification component. Okay, so they will provide us UVC component with the sequences. There will be sequences in each IP, so we no need to bother about designing of everything. We directly take the sequences. Our main task is to connect all the sequences to one particular sequence, all physical sequences to one sequence. That is what we call virtual sequences. Okay, so here from APB we will consider one sequence, and AXI and AHB, whatever IPs are there, all these IP we will connect all the sequences to one virtual sequence. Okay, so through this virtual sequence we will drive the data to the sequencer. In sequencer also we will have the virtual sequencers. Virtual sequencer need to be connected with the virtual sequence. From the virtual sequence we need to connect with the physical sequence. Okay, suppose here virtual sequence is there, and here in the virtual sequence we need to design some sequencer, the virtual sequencer. This virtual sequencer, again it will be connected to the physical sequencer. So how this virtual sequencer is getting the data? This virtual sequencer will get the data from the virtual sequence. Okay, virtual sequence will be connected to the physical sequence. Okay, so this is a very complex diagram, but for simple understanding I just explaining this. So from the sequencer, virtual sequencer, to the physical sequencer, here we will get the data. Okay, so from sequencer through BFM model, through driver we will connect with the DUT. Okay, so sequencer is getting bus sequences, which is getting from IP vendors, and GPIO sequences are connected to this virtual sequencer. Through this virtual sequencer, the physical sequencer is connected, and GPIO BFMs are sent to the DUT. Okay, so this is how the virtual sequence or virtual sequencers concept will work. Everyone understood?
Yes, ma'am.
But how we are going to connect all the sequences into a sequence library? Because we will design one sequence library, we will put all sequences into that particular library. Through that, we will get the sequences to virtual sequence and connect to the sequencers. So how all the connections will be doing? So we need to focus on that. That is very important thing, even for freshers. Anyway, freshers also need to write some program in the industry, or even if you are working experienced people, we need to write the program for these kind of things. Okay, so we need to focus on these things majorly. So any doubts still here? Anyone? Okay, so still 10 minutes left. We can complete the RAL model. So coming to the RAL model. So what is meant by RAL model?
Register abstraction layer.
Register abstraction layer model. Okay.
Here we are depending on our sequencer in order to provide any sequence, and as well as we are providing in the form of bus transactions. But if you're dealing with the register level, if you are dealing with the register type of transactions, there is no need for the sequencer. We can directly provide our transaction to our DUT. And what are the changes occurring in our DUT that can be mimicked inside our register model? Those facilities available. By using this RAL model, by using the backdoor access, we are doing that thing. And we are having that front door access for the bus transaction as well by using sequencer.
Okay. So what is the difference between backdoor and front door access?
Here we are depending on the agent. In backdoor access, mostly we are not using the agent. That was the main difference, no?
In backdoor access, directly we connect the register model to the DUT.
Yes, ma'am. There also another adapter is also there that will be used to convert that bus transaction into register transaction and register to bus transaction. In order to interchange the data between the register and our DUT, and the collected data from our DUT to our register. That our register model also contains the exactly design, that mimic of our design. In order to update that, we are having another data.
Okay. Others, what about you? Okay, so first of all, RAL model. Before also we discussed, right? So in DUT, basically we transfer the data in terms of binary sequences. Okay, bus sequences. Okay, we never transfer data in terms of address. Address data, it's not like a normal address and normal data. Register models will be different, right? It consists of memory mapping, particularly memory fields will be there. So we need to design according to the memory fields, memory mapping. So register data will be different. So 0, X, something hexadecimal values, 0, F, A, something values will be like this with respect to the fields and memory mapping. Okay. By using a normal sequences, till now, whatever we designed by using normal sequences, we can generate a normal bus sequences like binary data or decimal data or octal data or hexadecimal data, not particularly memory or register related data. Okay. In every design, there will be a memory. Basically, every SOC contains a lot of registers, lakhs of registers will be there. Okay, so to verify those registers, we need to send register data from test bench to DUT. Okay, in system Verilog, we never generate the register data, but in UVM we can generate the particularly register data. Okay, so here is a sequence library. Suppose sequence library in the sense all type of register sequences, everything related to the sequences, we will have the information into this in this particular library. Okay, so another thing is a register model. In the register model, we will have one register mapping. In this, we have all register fields and how the data is considered, what data we need to do the randomization. Okay, and whatever the register sequences are randomizing here, register sequences are getting here, those sequences we need to send to the DUT. Okay, before that we need to send to the sequencer, because sequence need to send the data to sequencer. Before, for normal sequences, we never use any adapter like that. Okay, so what is the adapter here? Adapter in the sense, whatever the register data is there, that register data will be converted into the bus sequence. Register sequences can be converted into the bus sequence. Why? Because to drive the data by driver, it never understand the register sequences, right? A driver will drive only binary bus sequences because all these are bus connections. Okay, so that's why adapter will convert the register sequences to the bus sequences. Okay, through the sequences, the data will be sent to the driver and driver will send to the DUT. So the adapter will be convert the register sequence to bus sequence to register sequences. Okay, so this is what a front door access. Backdoor and access in the sense that directly the register model will be converted to the DUT. Okay, so we need to know about both and how to write the program. That is important. Okay, so this is how some more brief diagram about RAL model. Okay, so first we have the RAL model here. In RAL model, if you see in a DUT, in DUT we have register A, register B, register C. So to verify this register A, B, C, we need to send the register data. If we send binary data, it never accepts. We need to send the register data. It accepts, but it's not much efficient. Okay, so if we send proper register data, then we will get the proper data in terms of memory mapping, the address and particular data. Okay, so that for that purpose, in the register file, we have the same registers here, ABC. We do the generate the sequences, register sequences that will be sent to the adapter. Adapter will convert the register sequences to normal bus sequences. That sequences will be sent to the sequencer. Okay, sequencer will be sent to the driver. From the driver to DUT, DUT to monitor. Again, this monitor need to send the data to the register data, because register model will store the data from DUT. Whatever the data is getting from DUT, it will store the data. Okay, updating. Always it will try to update its registers. Okay, so whatever the data is getting from DUT, we need to send to the RAL model library. Okay, so for that purpose, we use a predictor. Predictor means it is sending from DUT monitor to RAL model. In predictor also we will have the adapter. Again here adapter will convert whatever the bus sequences are getting here. That bus sequences will be converted to register sequences here. That register sequences again it will be stored by the register model here. Okay, so this is what we call as a RAL model. Clear everyone? Any doubts still here? At the same time, to this monitor, we can convert the scoreboard, checkers, coverage report files, everything we can convert, connect using analysis port. Okay. Any other doubts? So in this session, we have discussed on RAL model, virtual sequences, factory registration, configuration database, reporting mechanism, phases, TLM ports, difference between UVM and system verilog. Okay, so overview, I think I have given the overview of all the concepts, but these all are very huge concepts and internal sub concepts will be there. It's not possible to cover in one session. So maybe in future, if you are interested, you can enroll for some workshops or like that. So yeah, is there any doubts till here? Anyone? Any doubts? And from February 1st onwards, we are starting a workshop, advanced UVM workshop. Okay, this workshop is only focusing on lab sessions, real-time use cases of all the concepts. Okay, so regarding TLM ports or factory registration or phases, whatever, only concentrating on the lab sessions, not theory. Okay, so if you already know the theory and if you are not able to work on some practical things, if you are not able to understand the practical approach of UVM, this workshop will be good for you. Okay, so this is a 15 days workshop. 15 sessions will be there in 1 month duration. Every session is alternate days. Okay, so one day is live session, next day is for practice, assignment practice, and then live session, and then assignment practice. Okay, so in this 15 days workshop, this is the curriculum what we are going to cover. Day 1, day 2, day 3 UVM phases, day 4 TLM ports, everything in terms of coding only, not theory. Okay, so UVM configuration, register, reporting mechanism, and RAL model, virtual sequences, and finally designs. So we are going to work on different designs from day 11 to day 15. Total practical approach. Like first we are designing some blocks, digital blocks like registers, counters, adders, arithmetic logical units. So once those are completed, FIFO memory is completed, then AXI, finally VIP development of AXI protocol. What are the features and how we can verify the best features of AXI. So these are what we are going to cover in a 1 month duration of workshop. Okay. So if anyone interested, if anyone want to learn more in depth of UVM, you can prefer this workshop. Okay. And it's very affordable budget in 5,000 rupees for 999. So you can master your UVM skills from this workshop. Okay, and materials will be provided and tools will be provided. So yeah, is there any other doubts to anyone? And thanks for joining, everyone.
No doubts, ma'am. It was great down interacting with you, ma'am.
Thank you.
Have a good sleep, ma'am.
Thank you. Okay, thank you all. So if you have any doubts, further doubts, you can text me. Okay, we'll see in the next any live sessions or webinars, or if you enroll for workshop. Okay, thank you all.
Thank you.